Well, welcome to patient statistics. So hopefully you all are where you should be. There seems to be a problem with a little app thing. So just make sure that you know where you're going. So this is just like any other flight, a shared code. We have 364464 and 6004 and 6062 for the MSCs. And probably there's a 6162 somewhere. But it's all Bayesian statistics. Okay? So what we're going to do today, I will go through some of the admin bits and pieces. And after that, today, the rest of today and tomorrow, I will give a brief introduction and try to motivate the use or the reason why you will be happy to learn Bayesian statistics. And then next week, we will start doing the actual stuff. Okay? So just as I said, this is undergrads and MSCs. Lectures will be today in lecture theater 3, so you know that where that is. And Friday is tomorrow at 2 in lecture theater C, so undergrads would know where that is. For Nanjing students and some of the MSCs, you have to go outside Hicks, walk down, come back in, and then go one story up, I believe. That's a nicer lecture theater, so probably it won't be as cramped as today. Resources. So everyone has access to the course webpage. Hopefully I have, yeah. So that is that. Everything will appear there. So you have all the resources right now there. Exercises, past exams, code, solutions, everything will be posted there. In particular, now you have access to the lecture notes. So there you are. And the overheads, that's what I will be using throughout the course. There's this handout on distributions. That's quite important. You will have access to that handout in the exam, right? So that has most, if not all, the distributions that we'll be using throughout the course. And not only the PDFs, you will have the means and variances and some comments and some properties of them, right? So what this means is that you don't need to learn by heart the distributions, you will have access to them, okay? That will be important, and I will highlight why this is important in a second, but Bayesian statistics is basically probability. So that means that we will be doing loads of things with probability distributions. So just to be sure that you know what you're doing. So there's discrete distributions, some continuous ones, PDFs, means, variances, and so on, and some multivariate, okay? So you might be familiar with most of them, and there might be one or two that are, or probably will be new to you, okay? And finally for the materials at least, there's a problem booklet there. It's not order, so there's problems that will require you to know different parts that we will be covering in the course. But at least you have something to look at and probably have a go at different stages during the course. And I will post solutions towards week 9 or 10, okay? So that is that. MSCs, all MSCs, so that's 004 and 62, should have access to MOL through the 6004 webpage, okay? So if you're doing clinical trials, you will also use MOL for inference, okay? So make sure that you can access that. If you can't, just let me know and I will give you access, okay? You will have obviously the same materials. The difference is that there are MSc distance learners. So if you have any questions or queries, you need to ask them through MOL. So everyone in the MSc has access to the same information. Okay? Cool. Now, the awful part of assessment. This is where things are different for everyone, so I will hopefully be able to explain this. So for 364 third-year students, there will be 3 assessed exercises spread throughout the course. Each one is worth 5%, and then you will have 1 exam at the end of the semester worth 85%, okay? Exercises are usually quite simple, so I strongly suggest that you have a go and submit them, because that's almost 15 points for free, 15 marks for free. So please do it. 464, 2 exercises, 5% each, and then you will have a project. So this will be a bit more complex than what 30 years will do, and that's worth 20%. And then you will have an exam which is similar to the 364, that's worth 70%. Okay? Now, the complex part. Inference 6004. So half of the mark is for semester 1, half of the mark is for semester 2, and that's true also for 6062. If you're doing 6004, you will have 1 project in semester 1 worth 15%. And then you will have 3 assessed exercises worth 5% each in semester 2. Okay? And then at the end, you will have an exam worth 70%. If you're doing trials, then there's 1 project worth 15%, the same project as 6004. And then you will have a 2-hour exam at the end of the year, right? Which is 85% of that 50%. And then for semester 2, you will have 2 projects worth 30 and 70% of half of the mark. Is that okay with everyone? Yeah? Okay. Probably something I haven't said is there are some office hours. It's probably not very visible there, so the other way around. Those are my office hours. So Wednesdays, half 1 to half 3. I'm in this building, I-13. I will be away on weeks 3 to 5. So I won't have, obviously, office hours there, but there will be someone covering for me. So you can ask her. The same goes for MSc students. You can still have, can ask questions in MOL. You will just get answers from someone else. Okay. Fine, I think that is it. Any questions about admin stuff? Yeah? No? Okay, fair enough. So, as I was saying, I will today and tomorrow give an introduction to, it's more like a motivation to Bayesian statistics. So I will be talking quite a lot and probably not doing a lot of maths, but hopefully that will kind of give you some context of how, why studying and learning Bayesian statistics and doing Bayesian statistics in practice is useful and fun, actually. But well, so far you've learned what we call, or it is known as frequentist or classical statistics, and that's basically estimation, unbiased estimators, confidence intervals, and tests, p-values, right? So, and that seems to work okay in practice, so why do things differently? Well, the thing is that in some cases, this approach can be quite misleading in practice. So I have some examples of papers illustrating these. I'm just using testing as an example, but you can find similar problems with point estimation and interval estimation. So this is a Nature paper. It's not too old, 2015. And probably you're aware, if you've seen the news, science news at least recently, of this problem, being able to reproduce results in science. So go back, do the same experiments, get data, analyze the data, and basically arrive at the same conclusions, right? And usually that is testing something, whether a drug is useful or better than some other, and things like that. So people have been concerned about, at least from the statistical point of view, of how frequent statistics works in these cases, because it seems that for some studies, you can actually not reproduce the results that were published at some point. So this is one of such papers, and what I've highlighted there is that interpreting a study result from its p-value alone is basically not useful. It's spurious, right? Unless you have highly powered designs, that means unless you have loads of data. If you have loads of data, you have loads of information. So basically doing p-values is not useful. So there's this another one in Nature, a bit earlier than that. And here they're giving some context on how p-values came to be. And they were proposed by Fisher. Probably you've heard about him before. Famous statistician, but even more famous geneticist. And the claim here is that he started using p-values just as an informal way to judge evidence in favor or against a hypothesis. So it's informal. That means that it is not mathematically precise. It gives you an idea, vague idea of how much support against or in favor of something or a hypothesis the data has. But it's informal. You cannot derive proper mathematical properties from it. So that's what this means, which is not very good, actually, if you're a statistician. This is a bit older, but highlights basically the same thing. I cannot find myself, but well, I don't know what I did. Yeah? Okay, yeah. Highlights the same thing. P-values do not quantify statistical evidence. Okay, so there's, and so this, what probably I didn't say is that all these papers come from different fields. So this is from psychology, and the previous ones were from physics and biology each. So from different fields in science, there's a strong evidence now that p-values and hence frequentist approaches to at least testing are not fit for purpose. And this is a bit more recent. So this is indeed a statistical paper that claims the same thing. There's a problem with the p-values. But what I like about this is that it highlights the essence, at least, of what I think is Bayesian statistics, and statistics in general should be. The solution to dealing with p-values, or the approach to testing, is to move towards a greater acceptance of uncertainty and embracing variation. What that means is that normally having just one value to summarize or to summarize your decision is not enough, right? One value, p-value, 0.05, 0.01. It's not enough. It's just not enough to summarize what you know about the data. You need to give basically a better description of the uncertainty about what you want to describe. And hence, again, using probability distributions, right? So we will go back to that. Okay, so if we do not like or trust frequent statistics, what should we do? Well, one option, and the option that we will be talking about this semester, is Bayesian statistics. Okay. The difference, or the main differences between this approach and the Bayesian one, is the use of subjective probability in Bayesian statistics, and that's what I will talk about today, and Bayes' theorem, hence the name. Okay, so Bayesian statistics uses a subjective approach to defining or to using probability, and then uses that probability with Bayes' theorem in order to combine information, your subjective information, with information in the data, and try to describe your state of knowledge after learning something. Okay, so I will start talking about subjective probability, because that's probably you've seen Bayes' theorem. Hopefully you've seen Bayes' theorem before for events. So I will leave these for later, but most of you most probably haven't heard about subjective probability. Okay. So I will talk about that in a second. So as probably will hear at some point, some statisticians believe that Bayesian statistics is the correct way of doing inference. That's that's me. Other other people don't like it. Fair enough. And some people, the vast majority, are happy to use methods from either perspective, depending on how useful they are. And I think that's the correct approach. But just to give you a flavor of how strong some people believe Bayesian statistics is the way, I have this extract of a paper. This is in PNAS, that's the Proceedings of the National Academy of Science in the US. It's one of the best science papers in the world. Probably you've heard about gene and gene regulation. We know that genes code for proteins, and the way proteins interact in any living body define how this living body interacts with the world. And so this is key. Gene regulation is key to life. And these people, which is absolutely lovely, say that we postulate that cellular regulatory machinery, so what any living thing does to continue being alive, may evolve to perform Bayesian inference in some intracellular output. So yeah, evolution is Bayesian. You got to love that. Anyways, okay. So there's people that really, really believe that Bayesian statistics, and there's this kind of observations in different fields as well. But I think the most important message to take from these is that the Bayesian approach is becoming more and more fashionable, let's say, in science, and not only in science, in finance as well, and economics, because it has this ability, or gives you the ability, to combine information from different sources and in a coherent way. So gives you a unified framework to combine information from different sources and give an answer, a statistical answer, a distribution. And that is quite difficult to do if you're a frequentist. Okay, and I will try and explain that a bit better in a second or two. Okay, so first thing I will talk about today is subjective probability. Okay, and we start with what you know, the frequentist interpretation of probability. Right, you've seen this sort of or a similar definition of probability before. So you have n independent trials, identical trials, in which the event E can occur in each one of them or not. And then if you want to calculate the probability of that event happening, then you can estimate or calculate or define that probability as the ratio of the number of times that event happens with respect to the number of times that you repeat the experiment, right? So what this definition entails is that the trials are independent and you can repeat them. So you can repeat the trial any number of times in identical conditions, right? Now, consider this event, the probability that Trump will be reelected, right? So, thanks goodness, that is not replicable. So, you cannot repeat the election, the re-election any number of times. It is uncertain, right? So, you don't really know if it's going to happen or, well, whether it will happen or not. So, you can have a probability of that happening. Okay. So the very broad definition of subjective probability is your degree of belief about that specific event bounded in between 0 and 1, right? Which seems a bit non-mathematical, right? So it's my degree of belief. Think about the typical experiment, tossing a coin a number of times and calculating the probability of it falling heads, right? So we might all agree that unless the coin is biased, that will be 1/2 basically, right? And you can repeat that experiment a very, very large number of times. And if you count the relative number of times that the coin lands head, that will be 1/2. Right? So we can agree on that, but probably we will disagree on that probability. Okay? So the message that I wanted to convey with this is that frequentist probabilities, at least using the definition of frequentist probability, can be only applied for events that can be repeated in identical conditions, while subjective probabilities can be stated for any event, right? So that's the first advantage of using the subjective approach to probability. And if you think about this, I mean, most of the problems that you are faced with when you're doing inference or statistics are of this kind. If you think about, I don't know, economics, and you want to estimate the GDP growth of next year, well, that will happen only once, right? You cannot repeat next year and the same conditions of the economy a large number of times in identical conditions. If you want to calculate the return on an asset, same thing, right? So just as a concept, subjective probability seems to be broader than frequentist probabilities, and hence will give you an advantage when you are doing applied work. Okay? And in any case, applied work always entails some subjective judgments. If you think about your model, so you want to do, again, inference on the GDP growth of the UK next year, the model that you select for this GDP growth will be absolutely subjective. You will have to choose the model, you will have to choose the parameterization, you will have to choose the way you analyze that model. You will have to choose whether you estimate that with an unbiased estimator, if you use method of moments or what have you, right? So every single decision in applied statistics is subjective. So arguing that taking a subjective approach to probability makes the inference less worth or less useful might not hold. Okay. So this approach has been there for a while, but it was developed in the late 60s and 70s by quite a few people. One of them was Bruno De Finetti, and he wrote quite a few seminal papers, and one of those books is called The Theory of Probability. And again, if you look back at early books in Bayesian statistics, most of them are called Theory of Probability because you will end up, if you're doing Bayesian statistics, working with probability distributions. Okay, and that's what we will do. We will work a lot with probability distributions. Okay, so this is one of his seminal works, Theory of Probability in the 70s. This is the preface, first page of the book. And the first thing he says is probability does not exist, which is kind of, doesn't make much sense if your book is called Theory of Probability, right? So what he meant by that is that probability as an objective thing, as a physical thing, is it's a bogus concept. It does not exist, and actually compares that to the existence of witches and cosmic ether and absolute space and time, right? And the important thing is that, and this is similar to the first paper, well, one of the first papers I showed you, saying that probabilistic reasoning should always be understood subjectively. It's merely stems from our being uncertain about something, right? So it's our uncertainty that makes statistics useful. If we were not uncertain about something, then we would not need statistics and we would not need probability. So our uncertainty is what should be modeled by probability and then used in statistics. Okay, any comments so far? No? Okay. So there you go. So we want to use subjective probability. So we, each one of us, will need to come up with a way of assigning a probability and later on a distribution to an unknown event, right? Or an unknown parameter if we want a distribution, right? So how we do that? How do we measure our subjective probability about a certain event E? So one way would be direct measurement, okay? So this is frequentist statistics. You have an event E, and then you can choose R red balls in the back of N, and then vary R and N until you judge that that probability is that ratio. So you could do that if the event was repeatable. But again, if we don't have events that can be repeated, this is not very useful. A better way is by doing bet fairs. Fair bets, sorry. So we can bet on E happening. Again, think about the probability of Trump being reelected. So the bet is you gain £1 if it happens, and you lose X pounds. So that's what you're willing to bet if it doesn't happen, right? And then you will choose X, what you're willing to lose, in such a way that your expected winnings, your expected earnings are 0. And that's what we call a fair bet, okay? So if we solve for that, the probability is basically, well, X over X plus 1, and X, if you've ever betted in your life, those are the odds, right? That's what you see all the time in the telly about betting, odds of this to that are ways of representing a subjective probability. Obviously, gambling companies will not make this 0. They will make that a little bit positive, slightly positive, so that in the long run, they will have some earnings, right? But this is used in practice a lot, and you can make money out of that. Okay? So there's a way that works for you to assign your subjective probability to basically any event. Okay? It can be more or less difficult, granted, but it is mathematically possible, okay, and practically doable. So what I will go through now is just to try and well, I don't know if convince you is the word. Well, I'll at least convince myself that this way of calculating probabilities is mathematically sound, right? What we like, if we're mathematicians, we would like the probability to have mathematical properties, okay? So we know the probability that we know, it's a measure, and it's a measure that it's bounded between 0 and 1 and has some, and behaves in some certain way, right? And out of those properties, we define distributions and means and variances and all these kinds of things. So we would like to do a very similar thing with our subjective probability. We want our subjective probability to be a mathematical entity, a mathematical probability, okay? So I won't bore you with the details, but what this means is a way of making operational the definition, the definition of subjective probability, okay? What you need for doing that is again, it's again bets. You want to be able to define or to judge whether two events are more probable, if one event is more probable than the other one. A is more probable than B. Okay? Sorry, A is not more probable than B. So you want to give an operational definition of that. And the way of doing that is again with bets. So you have a bet where you have two outcomes. The first outcome is to gain £100. It could be £1. It doesn't matter. And the second outcome is that you don't gain anything, right? And then you compare these outcomes with the event of B occurring or A occurring, right? And whenever you choose one over the other, means for you that you would judge this one to be more probable than that one, right? So this is again just a mathematical way of formalizing how to construct subjective probabilities on events, okay? Once we have that way of constructing probabilities, then we need to, as any mathematical theory, give some axioms. So the three first axioms are definitely necessary. The other two are a bit more technical. But again, you don't need to worry too much about the maths of this. This is just for you to be convinced that this is mathematically precise. Okay? So these axioms basically are telling you that you are able to say that one event is more probable than the other, or the second event is more probable than the first, or they're equally probable. And that any event has probability larger than the null event and smaller than the event of anything happening. And then these two are just technical axioms that will allow you to calculate conditional probabilities. Again, don't worry too much. But if you agree that these axioms make sense, then it is possible to prove, and that's what De Finetti and people like them did back in the 70s, that your subjective probability behaves like the measure that you know as probability, right? So your subjective probability can be represented by any distribution that you already know, okay? So that means that you don't need to learn new maths. If you know probability calculus, then you can do Bayesian statistics, okay? So again, this will not be in the exam. This is, again, just to give you some background on why using Bayesian statistics is not only useful, but it's mathematically sound. Okay? Good. Cool. So just a couple of things. That, well, again, just to make things a bit clearer. Now we know that your subjective probability is a mathematical probability, right? That's very good. Now, if we want to treat or we want to understand or to include the concept of stochastic independence, then we can look at the way it is defined in a frequentist way or your usual way. Traditionally, you say that if the probability of A and B is the product of the marginal probabilities, then they are independent, right? In Bayesian statistics, you say that A and B are independent if your probability of one event does not change when you know that the second event has happened. Again, if we go back to the Trump example, you would need to ask yourselves whether, I don't know, the knowledge that this, what's the name, Kavanaugh, this chap, probably will not be appointed to be a judge, whatever he's going to be, will affect your assessment of the probability of Trump being re-elected, right? If it doesn't change, then those two events are independent for you. If they change, then those two events are not independent for you, okay? All is subjective. This is a less controversial example. You have scores from two randomly selected students, and we're asked whether you think that X1 and X2, the scores, are independent. If you know from last year's, if you learned that someone scored, I don't know, 85 in the exam, in the Bayesian exam, would that affect your judgment of a second person? Would you think it will be around 85, right? So that's what I mean. That is your personal judgment. What is the basis, actually, for modeling in Bayesian statistics is not independence. That's why I'm introducing this here now. But it's exchangeability, okay? And this is a bit more complex, but it's much more powerful than independence, okay? So think again about these two exam scores example, right? So before knowing the actual scores, would you think that the probability of the first score being larger than the second one will be the same, will not change? If you take the permutation, if you think about the probability of the second score being higher than the first one, right? Or the probability of the first score being smaller than 50 would be exactly the same as the probability of the second score being smaller than 50, right? Or any other probability statement in which you swap the indices 1 and 2, right? So if that is the case, if the joint probability, in this case of x1 and x2, but if any sequence of unknown quantities, is exactly the same if you switch the indices, if you permute them, then those events are exchangeable, right? And the important thing about exchangeability is that exchangeable events have the same marginal distributions. What that means that if the events are exchangeable, then they are independent, right? So any sequence of IID, random quantities, is exchangeable, okay? And this is the main concept in Bayesian statistics. It will. I know that now it's a bit blurred, but it will become apparent why these differences are important when we do the Bayesian updating, right? When we have what we call hierarchical models. But for the time being, again, this I won't ask anything about exchangeability in the exam. This is just giving you context on technical concepts that are useful for Bayesian statistics and make it a rigorous mathematical concept. Okay, so I've babbled a little bit about how you can construct a valid mathematical theory based on subjective probability, right? But then why is this useful actually in practice? Why being a Bayesian, or at least a subjective probabilist, makes sense in practice? So, typical example, you've all done this before. You have data from a Gaussian with mean theta and variance 1, and you have one observation, right? You want, the only unknown quantity here is theta, so you want to make inference on theta. Theta is unknown, okay? So you get x equals 2, and you report a confidence interval, right? So x plus minus 2 times the standard deviation, 0 to 4, right? Roughly. So how sure are you that theta is in 0, 4, right? Can you say anything about that if you're a frequentist? Because that's what you're interested in, right? You're interested in whether theta is there or not. So if you repeated the frequentist interpretation of confidence intervals tells you if you repeat this procedure a large number of times, then 95% of the intervals will contain theta, 5% of the intervals will not contain theta. But that tells me nothing about my interval here, right? Theta either is there or not. So that is not a probability. Okay. So as a frequentist, you can say nothing about the probability of a parameter being somewhere because the parameter is fixed. There's nothing random about the parameter. And if you're a frequentist, that's where probability lies. But if you're a Bayesian, and that's again coming back to what is important about uncertainty, is that you are uncertain about theta. Theta is fixed, yes, but you don't know theta. You don't know the value of theta. And you want to quantify your uncertainty about theta. So if you are a subjective probabilist and use Bayes' theorem, you are able to do or to issue statements of this type. The probability of theta being in 0, 4, given that I observed the data, is such. And that practically makes a whole difference. Now you're able to say that you have probabilities of theta being in 0, 1, or the hypothesis being true, and so on. Things that you cannot do in frequentist statistics, and you have to go around saying that if you repeat the experiment a long number of times, then this will happen. So those interpretations go away, and you can do probabilistic statements about unknown quantities. And so this is the summary of what I've just said, and this is the important thing in practice, and that's why Bayesian statistics is more and more often used in practice in science. If you're a frequentist, what you can say, or any probabilistic statements that you can do, are about the data or statistics, x bar, s squared, given the parameters, given theta, given sigma square, right? But this is not what usually people are interested in. People are interested in, you already observed the data. The data is fixed. The data is your sample. So I've already observed that. I'm not going to repeat the experiment. If I repeat the experiment, I probably will get something else. What I want to say is, given that I have that data, what can I say probabilistically about the parameter, about the unknown quantity? If you're a Bayesian, you're able to say this. Okay? And that's, if you ask me, a certain difference. Okay. So just to start talking about these, and I will leave you with that. This is the second part of Bayesian statistics. And these, we will be doing this all the course, okay? So it's important. This is Bayes' theorem. You have seen Bayes' theorem with events, right? But Bayes' theorem also holds for distributions, okay? So in here, you have a distribution on theta, given the data. And in the right-hand side, you have a distribution of the data given theta, right? And then you have these two new chaps that probably you haven't seen before, okay? But this is Bayes' theorem. So when you multiply these two together, you have the joint distribution of theta and x. If you divide by the marginal distribution of x, then you get the conditional distribution of theta given x, right? Bayes' theorem, pure and simple. What happens in Bayesian statistics is that we have specific names and roles for each one of these quantities or functions. Pi of theta, this guy is your prior distribution, right? And this is what this encodes. It's a distribution. It's a probability distribution on the unknown parameter, right? So this is a distribution that will describe your knowledge about that parameter without seeing the data, okay? This is the likelihood. This is your model. You're familiar with that. If the data is Gaussian, this is the product of n Gaussians with unknown mean and variance, whatever, right? And what you get out of multiplying these two and then dividing by f of x is the conditional distribution of theta given x, and that is called the posterior distribution. That posterior distribution combines what you know about the parameter without seeing the data, what the data is telling you about the parameter, the likelihood, and converts that into a new distribution. It's a probability distribution on the parameter conditional on the data, and that is called the posterior distribution. And that encodes all you know about the parameter after observing the data. Any Bayesian solution goes through the posterior. You will be dealing with distributions day in, day out, okay? So if you can't